Welcome to the third video in the Day of Datomic training series. With the basics out of the way, in this video Stu Holloway turns to the Datomic transaction model. We'll see how Datomic is an old-school ACID database and at how Datomic allows you to group datums together into entities. Stu will also discuss how Datomic handles identity and the related question of uniqueness. Finally, Stu will cover database functions that run inside of a transaction.
Welcome back to the Day of Datomic afternoon portion. This morning we talked about what Datomic was, and we talked about how to model information in Datomic. And you've worked on creating a schema and putting that schema into Datomic. Now we're going to talk about actually putting data in. So because Datomic schema is itself transaction data, you've already done a little bit of this, but we're now going to explore it in significantly more detail. But before we do, and as people are winding their brains back up to full activation levels after their lunches, does anybody have any questions left over from the last lab and installing schemas into the system? Great. OK, so I'm going to start by talking about the ACID properties of transactional systems. Historically, this has been a big deal in relational databases for good reason, and Datomic supports these properties. The atomic property of transactions means that the transaction happens in its entirety or not at all. Right? So there's no sense in which you can ever be in a situation where half of a transaction happened. And the example people always use to motivate this is, we were doing a financial transfer, and the money disappeared out of one account but never appeared in the other one. That's a really bad half of a transaction to have happen. The C in ACID stands for consistent. And I would encourage you to go and read the full docs on this. But the sort of one-sentence summary is that every Datomic process sees a global ordering of what happened. Right? That's what it means to be consistent. So I see events happen in this order. You see events happen in that order. This is contrasted with, say, eventual consistency, where you don't see things happen in the same order. This is an enormously important property in writing systems that are easy to reason about. Isolation. Datomic is isolated trivially because it's a single writer system. Right? There's nobody to be isolated from. Right? There's only one person doing the job of writing, only one thread in one process doing the job of writing, so isolation comes trivially. Isolation is something to worry about if you have a system that's trying to speculatively do multiple things, one of which might finish, I'm going to be halfway through with this and halfway through with that, and then one of them is going to finish. But maybe the one who finishes first is going to be able to see work from somebody else who is halfway done. Everything happens as a set, and it all happens on a single writer. So Datomic is trivially isolated. And then durability. People sometimes get a little bit worried about this. Durability does not mean that your data is going to be guaranteed to be there. Let me just say that again. Durability does not mean that your data is guaranteed to be there. Right? If the Earth's sun goes supernova, your data may not be there. If there is an earthquake at the data center where you store your data may not be there. Right? There are things about making sure your data are there that are operational things, I guess is the point that I'm making, that are not about the functioning of your system. And what we're meaning when we're talking about durability here is that the system always flushes through to durable storage before telling anybody that the transaction was done. Systems will cheat on this in order to appear to write faster. Right? So every one of these properties is something that people are maybe tempted to cheat on for write performance reasons. Right? So I'm going to go ahead and write half the transaction because I have it right now, and then I'll have less work to do later. Of course, if I do that, I might break atomicity. I'm going to have multiple people working at once, but oops, I might break isolation. It takes a while to wait for the disk to say it's on the disk and I've got it. So once I've sent it to the disk, I'm going to turn around and tell the user I've got it, even though I haven't heard back from the disk. That's obviously a path to breaking durability. Right? All of these properties, and the reason why these properties are grouped together and got an acronym to begin with, is that all of these properties are about making a system that works reliably, predictably, and understandably. And Datomic is an ACID system. And in fact, Most ACID systems, many ACID systems, have all kinds of knobs where you can tone this down so that you can try to push more writes through the system, and we just don't. Right? We don't believe in it. We believe there's a huge value proposition in having ACID, period. Not ACID maybe, or if I'm trying to win some benchmark game, I can flip this switch. I don't know if anybody's ever looked at database benchmarks, right? But it's a total mess, right? I'm going to flip this switch, which says, don't acknowledge writes from the disk. Well, of course I can write a lot faster if I don't actually have to write. So there's no gaming here. This is straight up. We want to make sure we know where the data is and that it looks a certain way. Now, the way that data gets into the system is via the transaction API call. And the transaction API call is just going to take a connection and a list of new information to put in the system. And the primary forms that information can take are adds and retracts. So an add is going to be the keyword db add, followed by the entity ID, the attribute, and the value. The retract is going to be retract, followed by the entity ID and the attribute and the value. Now you'll notice that these assertion and retractions are 4 tuples. What am I doing? What entity am I doing it to? What attribute and what value? There are 4 tuples here, but Datomic makes what? 5 tuples. So which part of the tuple is not here? Transaction. Who's in charge of that? Datomic is, right? The transactor is in charge of making that choice. So you're saying everything you possibly know here. I want to say these 4 things. Datomic is going to say the 5th thing and make datums for you. One thing that you will quickly discover when building transactions this way is that you often want to make a bunch of assertions about the same entity. So I want to create John Doe. I want to assert first name John, last name Joe, email John Doe at, phone, blah, blah, blah. I want to have something that looks not so much like a datum, but more like an entity. And so the transactor and transactions in Datomic also support entity maps. So entity maps are just a way of concisely saying, I want to make a bunch of assertions about an entity. This is a mechanical thing. Remember I said before that once data is in the system, from datums you can infer entities? This is just the other side of the coin. Right? When I'm putting data into the system, I could put it in the shape of entities, and Datomic can infer datums. So this is entirely a mechanical thing. And here's just an example showing going from one to the other. If I wanted to say that there is an entity 42 whose name is John Doe and who likes pizza, I could have 3 assertions. Add likes pizza, add first name John, add last name Doe. Or I can create a map where I have dbid, which indicates the E, likes first name, last name. Test your knowledge before the question. Is it possible to do retractions with these entity maps? No, because there's no way to hang, there's no place to hang them. Right? They're keys and values. There's no extra place in a map. Right? The keys are the A's, the values are the V's. There's no place to put the op. Right? So there's a presumption of this is adding assertions, not retractions. Yes?
What if an attribute is a cardinality many?
So if an attribute is cardinality many, then you can just have multiple of these.
Yeah, for the entity map.
And in the entity map, then you can pass in a collection if you want for that value, and then all of those values will be added. So good question. If the thing is cardinality many, you cannot put a collection in value position in the list form. This is the bottom thing that Datomic processes. But when you're doing entity maps, you could have a collection, like let's imagine that John's allowed to like multiple things. That could be a collection of strings. And then that will expand into as however many datums as are in that collection. It is possible to simultaneously add multiple new entities that refer to each other. And so here we're going to create Bob and Alice, who are spouses. And so now you're going to see the dbid literal, and we'll talk a little bit about more these literals. So the dbid literal says, I'm manufacturing a database ID, a temporary ID, for something I don't know is in the database yet. And that dbid literal, it's an Eden extension. Remember we talked about how Eden says you can just arbitrarily say, I've got a named thing? I have a named thing here called a dbid. DBIDs have 2 components, a partition, which we'll talk about more in a minute, and the actual number or the ID of the thing. And the numbers are entirely up to you. The numbers from -1 to -1,000,000 are reserved for your use. If you need to have more than 1,000,000 IDs in your transaction, you need to have a smaller transaction. So that's why that number is limited there. So here I'm saying I don't know what Bob's ID is going to be. Right? I don't know what Bob's going to be. The system is going to assign Bob an E, but I'm going to call Bob user minus 1. And I'm going to call Bob's spouse user minus 2. And then down here, when I'm talking about Alice, I'm going to say Alice is going to be user minus 2, and spouse is going to be user minus 1. So all the negative numbers mean whenever you pass a negative number like that to Datomic, you're telling Datomic, this is a temporary ID. You assign the real ID. You're going to get back a positive number. Yep. And then these things can nest arbitrarily. So for the canonical example of I want to create an order with a bunch of line items, I can have a map for the order, and then the order line items key is cardinality mini. So this gets back to the question that was asked before. And I'm going to have two things in my order. I'm going to have one chocolate and two whiskeys. So I have an entity for the chocolate portion of the order and an entity for the whiskey portion of the order. So this is really nice. This allows you to compose really substantial jobs, really kind of almost anything that has relationships, to other pieces, and pass it in as a single piece of data. This also encourages a style of programming that treats the transactions themselves as a piece of data. Which means that most people, when you write a Datomic program, you end up with something that makes transaction data, but hasn't actually sent it to the transaction yet. That's a really important separation, because imagine that you're writing a unit test. You can write a unit test for a function that makes the transaction data that doesn't interact with the system at all. Right? There's a nice level of decoupling. Another thing to imagine there is imagine that right now you're putting stuff directly into the system, but 6 months from now you have a change of requirement, and the transactor is not going to be presumed to be available. So you're actually collecting data on a mobile phone, and then later it's going to sync up with the system. That thing could make transaction data and store it as Eden, and then later when the system is available, you submit the transaction data. So encouraging you to think about data as opposed to think about operation. Like it's not do, it's make. Right? I'm going to make some data that gets added to the system. Yes?
Would you ever merge past transactions, like say you have two mobile devices, and they both have created some Eden data, and then they record the time at which they're created, and then they get merged in?
So the question is, would you ever merge? Datomic is an ACID system of record database. So it is going to have an order at which you recorded things. If you want to build offline things, if you want to take the example that I just did and record time information about when things actually happened, you need to keep a different attribute. Because that Datomic is going to say, well, those both showed up at sync time tomorrow morning at 9. Right. And this comes up in other ways as well, right? You're going to have situations that are bi or multi-temporal, where Datomic's time of record is one form of time in the system, but your effective at time is something else. And you're going to add time attributes to model that.
So the time that it'll order them is the time of the serializer.
They are ordered by the transactor. The transactor is in charge of order in the system. Right? You don't get to influence that. You can't cheat. You can't go back in time and say something happened yesterday, because something didn't happen yesterday.
So it's whichever mobile device sends that information first is the one that will be first.
That's correct, right? It is literally that. It's an ordering. I mean, the transactor really is an ordering system, not an ordering system like you make orders from an online store. It's a system that puts things in order, and they are put in order by arrival strictly. That's the reality of it. Yes.
So for the deferred right, does the transaction ID get created when the transactor actually creates it, or when the transaction is created?
That's correct. So as you're probably surmising, if you're going to make transaction data and then write it later, then the actual transaction, the entity IDs that are created by that transaction and the transaction ID are going to be made when the transaction executes. All right, now we will finally talk about partitions. We've seen partitions, and I've waved my hands at them. We've seen db.partUser, just on the previous slide, as the partition component of a temporary ID. We saw db.partDB, which is the partition where you were instructed to put things in schema. But what are these partitions? Partitions are a grouping mechanism, and they're a very interesting grouping mechanism. Imagine that you had a set of file cabinets in your office. And one of the file cabinets was for HR records, and another file cabinet was for customer orders. And now imagine that you tried to translate that into a relational database. Every one of your file cabinets would represent more than one table. in the database, right? It would be coarser grained than a database because you would have the employee table and the employee equipment table and whatever, and you'd have the order table and the line item table and the join table and so forth. But there's a higher level concept of a whole bunch of things are related together. The partition is kind of like the file cabinet level of thing in Datomic. Now, that being said, it doesn't really say put this in one file cabinet and put that in another file cabinet, but it does say, it acts as a hint to indexing and says, I want to group certain things together. And this will help locality for your queries without otherwise affecting transaction semantics. And so here's an example. So this is, and I apologize for this being a little bit small, but I wanted to get more information on the screen. This is a table produced from some sample data that you can go and run and reproduce yourself. So if you run this query at the bottom, which is in that Day of Datomic project, you can actually produce this data. And what this shows is I'm showing entity, attribute, value, transaction, and added. So the 5 things to the right are Datomic datums. But I'm also showing you the partition. And what you're going to see here is that the partition actually corresponds to bits in the datum. So the 0 partition doesn't produce any bits in E. But the 3 partition shows up as the letter C here. All these guys in partition 3 are here. And all these guys in partition 4 are the 1 here. So the partition acts as a bit mask in certain parts of E. And because it's at the high part of E, what does that do to your E-based sorts? Everything in partition 3 is where in an E-based index? It's all contiguous. Everything in partition 4, it's like being in a different file cabinet in that sense. And what this does is it allows you, if you know when you're first devising your system, it allows you to say, you know what, I'm going to put the employee records in the employee partition, and I'm going to put the customer order records in the customer order partition. And then if you later have a system that's only working with the customer orders, then it's going to have much better locality of reference when it's pulling the data. So that's what's going on with partitions under the scenes. There's nothing especially magical about it, right? Partitions act as a component of entity IDs. There are 3 partitions built in. db.partdb is required for schema entities. That's the only thing you should put there, and you must put them there. db.parttx is for transaction entities. You cannot put things in the transaction partition. Datomic puts transactions in the transaction partition for you. And then db.partuser is for your own entities, except that you're encouraged to maybe make your own partitions when you're starting to do a more serious design for your system. And so here is creating a couple of partitions. Creating partitions is adding data to the system, just like creating attributes was earlier. And so here I'm going to install a partition called inventory, and I'm going to install a partition called customers. Having installed those partitions, then in the future my temp IDs can refer to those. Right? So when I make a temporary ID, it can take inventory or customers as that first argument instead of db.partdb, db.partuser, whatever. Questions about partitions? By the way, you can totally ignore partitions. Right? You could put all of your data in the db.partuser partition and all your schema in the db.partdb partition and just forget about it. Right? This is entirely, in that sense, it's somewhat of an advanced concept. Yes?
So the partitions kind of preserve part of the entity
Address space.
Yes?
Yes?
So what's the size of the entity address space?
The size of the entity address space is 2 to the 42 or 2 to the 44 or something like that. And that acts as a hard limit on the size of Datomic systems. You'll see that that's a pretty big number when you do the math. But yes, that is one of the ways in which Datomic has an upper bound on size. Identity. Some things that go into databases have practically no identity. So if you were recording events, right? The events don't have any primary key. They just mean that something happened. But a lot of things in systems are going to have interesting identity. And Datomic provides you sort of 4 different conceptual things dealing with entity. The first one is everything in Datomic has identity by its entity ID. Right? Datomic assigns entity IDs. It does this in a very efficient way. They are stored in a data type that's very efficient, a 64-bit long, which hardware knows how to deal with very well. And you get that for free. The weakness of the entity ID is that it's relative to a database. So there's no global uniqueness guarantee about that. It's an ID that's particular to the system. Depending on your experience, you may have been instructed in working with databases never to expose database internal identifiers to the outside world. Right? There are people who just forbid that, and there are reasons that they do that. Right? These are kind of opaque things. So you might have a requirement that you don't expose these kinds of things to the outside world. A lot of things have IDs that are dictated by the outside world. Right? So social security numbers, email addresses, phone numbers, any of those, SKUs, any of these things that are synthesized unique things in the world. The way you represent those in Datomic is with an attribute that's marked db.uniqueIdentity. And then typically, Datomic doesn't require this, but typically the value type of that's going to be a string or a UUID or a URI. Right? It's unlikely to give something a unique identity that's a Boolean. Right? That would be goofy, right? There could only be able to be 2 of them and so on. So typically it's going to be a string or a UUID or a URI. Now, the other thing that sometimes happens is that you have a requirement that certain entities in your system have globally unique IDs, but there is no externally provided one. Right? These entities don't have SKUs. They don't have email addresses. They don't have whatever. So it's your job to provide one. When you're in that situation, the appropriate way to do it in Datomic is, again, to have an attribute that's db.uniqueIdentity, and that is of type UUID, but you need to use squids. And what squids are, jumping ahead a slide, Datomic has an API called squid, and squid will return a UUID that is indexer friendly. And the problem is UUIDs are brilliant, except that typically generated UUIDs are randomly distributed enough over the possible space of UUIDs that they're a catastrophe for indexers. Right? Because what's the worst possible data to index? Right? Purely random data. And you'll see this in other databases as well. Datomic is not the only database that does this. You'll see that lots of databases have their own APIs for making UUIDs, and the only thing that these APIs are trying to do is make UUIDs that are more indexer friendly. And the way they do it, I mean, Datomic gives it away in the name. They're semi-sequential UUIDs. So they're not sequential. That wouldn't be random. They just were a straight counter. But they are sort of gradually mostly sequential, so that you don't have problems for indexers. And then finally, sometimes you want something to have a programmatic name. Sometimes you want something to be a literal that you can refer to in your program. The example of this in Datomic is schema. Right? Your attributes and your partitions and all these things you've already seen, these all have keyword names. Those things have type db_ident, and when something in Datomic has a programmatic name, you can use that programmatic name in lieu of its number. And you saw this before when we were looking at data in the console. Sometimes the E column has keywords in it instead of numbers. Right? You see, and in fact, we can go back and look at that. Let's see. So, what was the query that we did that was good for that? We can go grab all the country names, and you'll notice here that the E for country name is reported as a keyword, not as a number. What that means is that that entity, it has a db_id still, but it also has db_ident. db_ident is very special. Right? db_ident allows you to provide a programmatic alias that Datomic will use in lieu of the number. Right? It gets you out of the business of reading the ugly numbers. Right? It's also really fast. Right? It's constant time lookup to convert from a number to an ident or an ident to a number. So, why shouldn't you just use these for everything? This is a good test your understanding question. Think about it for a minute. Why shouldn't you use, let me describe the characteristics of this thing as, again, right? Numbers are hard for humans to deal with. So we can give things semantic names. Datomic has a first-class feature for doing that called idents. You can do this with anything, right? This doesn't have to be schema. We've seen it used for schema. In fact, here it's not schema. Here countries have all been given, semantic, human-readable to some degree names. Doing this gives you constant time lookup between ID numbers and their programmatic names, and constant time lookup between programmatic names and their numbers. Something about what I just said. Constant time lookup. These things are all stored in memory. They're all stored in a direct table in memory. So if you put your whole database in that, what's going to happen? Bleh, right? It's not going to happen. The other thing is that semantically it doesn't make sense. Most databases are not full of things that have programmatic names. Right? You don't have a variable in your program for every row in your database, a named variable that uniquely identifies that row. You have names for occasional special things. So you're not going to use this all the time, but where you want to use it, it's a cool power. So the last thing we're going to talk about with regard to transactions is, and this is the advanced part, is transaction functions. So there's a little bit of a problem with the happy world I've painted for you, where everything is made up of adds and retracts, or maps that get turned into adds and retracts. And the problem is, John likes pizza, John likes ice cream. Now we have, I want to add $10 to John's bank account. Well, what happens when I do that? I go and look at John's bank account. I see that it's 100. I then create an assertion that says John's bank account's now 110, and I send that to the system. What could possibly go wrong with that? I don't have global control of everything that's going on, right? I don't have stop the world control. So while I was thinking about adding 10 to John's balance, what did somebody else do? They subtracted 100 from his balance, and then I came in and said it was 110 again. So in order to deal with this, we need some way to say that I want to know what the value of the balance was at the time the transaction was applied. I've already said Datomic is a single writer system. There's one thread on the transactor that does the applying of transactions. So who is the only possible thread in the system that can do this job? That thread, right? The thread on the transactor that does this job. And so the way it works is you are allowed to define arbitrary keyword names beyond add and retract. All right, so I can define an arbitrary keyword name called inc that says increment this. And if I just sent a transaction to Datomic like this, Datomic would say puke. I don't know what inc means. Right? I only know add and retract, but Datomic provides a mechanism for you to teach it what inc means. And that's called transaction functions. And so the idea is you can write what's called a data function that's going to run inside of the transaction. Inside of the transaction, that function is going to get passed the value of the database at that point in time. That's the magic important thing, right? That's what we want to know that we couldn't know from our side of the world. We have to know what was the actual value of the database. And so what that does, the job of a transaction function is to do something that's kind of like macro expansion. It takes inc John balance 10, it looks at the database and sees that the database currently has John's balance at 100, and it spits out db add John balance 110. Whenever Datomic sees data with a transaction function in it, it's going to look up that function in the database, call that function, and then substitute in whatever data that function returns. This is a recursive process. So that function could actually return data that indicates another transaction function, and then that could return data that indicates another transaction function, and so on and so forth. Interestingly, there have been at least 2 questions from the class during the breaks that this could be used to answer. Someone said, could I encrypt data on like a per attribute basis? Not with raw asserts and retracts, but you could have a transaction function called encrypt that took an entity, an attribute, and a value, called an encryption algorithm, and then put the value encrypted in instead of the original value. I'm not saying that's the best way to do encryption. I would think maybe a more systemic, let's encrypt the whole storage, might be a better approach, but you could do that. The other question from the class that this could address is somebody wanted to have basically composite keys. Right? Datomic doesn't do composite keys, but if you had a relatively modest need for them, you could say, I'm going to write a transaction function that takes more than one key, looks them all up, and sees if there's a collision, and then throws an exception if there is. And there's actually an example of that in the Day of Datomic sample project. So if you're interested in that use case, there's an example there. But those are kinds of candidate use cases beyond increment, which is an obvious use case. So here's how this works. Inside, when the transactor sees inc, the transactor calls entity inc, it grabs that entity, and then it gets the DB fun of that entity. Datomic can store functions natively as a type, obviously, because now we're like installing them and doing that. It's then going to call that function, passing in the current value of the database and whatever you gave it, right? So John account 10. And then the job of that function is to produce data on the outbound side that should go back into the transaction. So here, db add John account 110. So here's an actual implementation written in Java. So here's what we need to do. We're going to write a function that takes a database and an entity and an amount. We're going to look up the entity and some particular attribute on that entity, which is probably should have been an argument here. We're going to calculate a new balance and create an assertion and return a list containing an assertion. I'm now going to show you what is arguably the most magical thing in the whole course. Not magical like sneaky and mysterious, but awesome. Let me use the word awesome instead. The most awesome thing in the course. Datomic is so, data orientation in Datomic is so powerful that it can even take Java programs, which are naturally bloated, and make them really small and have the same shape as pseudocode. So this is notice that I'm writing this in Java. The Java implementation of this is going to be no longer than the pseudocode. Right? Given the database, look up the entity, then get the value at that entity and add the amount, then create a list that has db add in it, and E and A in the new balance, and then return a list wrapped around that. That's pretty cool. I never write Java methods that are that short. A couple of other things worth noting here. Java obviously doesn't have any idea about keywords. So db add is really a keyword. If you were writing it in Eden, it would be :db/add. Datomic automatically, out of friendliness to languages that don't have a keyword type, will take strings in those situations and convert them into the appropriate keyword type. Likewise, when you're doing gets from an entity, if you're coming from a language like Java that doesn't have keyword types, you can say get and pass in the string form of a key and get back results instead of a keyword form of a key.
Is there still room for collisions here? Like, I remember vaguely something sending the previous information as well just to make sure. Doesn't take on that.
So transaction functions give you all the power, right? If you write a corrupt, broken transaction function that makes bad decisions, then you can mess up your database. But if you write a good one, then you have all the power. You have the truth as of right now, and it's up to you to use that truth wisely. Now, one of the things that Datomic provides is it provides a built-in function called compare and swap, or CAS. And CAS says, you know, I don't want to go through the trouble of doing a lot of work in transaction functions, but I'm going to do something speculatively, and then I'm going to put this into the transaction. And if I find that the old value isn't what I thought it was, I will reject the transaction. So that's implementing optimistic concurrency using this capability. But that's still not going to result in a corrupt database. What it's going to result in is you tried to do some work locally, and then you said, do this if you agree with me that this is the current truth. And the transactor says, no, I disagree with you. That is not the current truth. Right? Things have moved on since then, so you shouldn't make that update. But that's another example, and that's a built-in. So Datomic actually ships with a small set of built-in functions for transaction functions. It ships with CAS, and it ships with retract entity. And what retract entity will do is it will take an entity and it will create a retraction for every datum associated with that entity. Right? Because otherwise, to get rid of an entity, you would have to look up all the datums and do a matching retraction for each one. And that retract is aware of both inbound and outbound references. So if somebody else refers into that entity, it will retract those datums. It's also aware of components. So if you retract a component, it will retract all the line items. But given what I've just told you about transaction functions, you could write either one of those yourself. Right? Using the data, Datomic's not doing anything magical that you couldn't do. Right? It's looking up stuff in the database and doing something like this.
Did you say that these are like stored procedures?
Well, so it's interesting, right? Are they like stored procedures? You can use these functions outside of transactions. So the database has the ability to store functions in it. You could look them up and call them yourself anywhere in any pure process. So in that sense, they're not especially like stored procedures, because stored procedures really run inside a database. These could be in your application, right? This could be in your own address space. So in that sense, they're kind of broader than stored procedures. On the other hand, they're also kind of narrower, because a lot of times you use stored procedures to do a bunch of work in the database because it's too expensive to do it in your own process. But in Datomic, the database is in your own process, so it doesn't make sense to write stored procedures to do those jobs. So it is code that's stored in the database, but the ways in which you're going to want to use it are going to be different than stored procedures. The place they overlap is when you have a stored procedure whose job is to enforce invariance in how data goes into the database. Right? That's where you're going to overlap. I should also mention that transaction functions compete for a single thread. Right? They compete for a single scarce resource. And so when you write these, you want to be very mindful of performance. And you want to be very mindful of not, I mean, this is a way to do accidental unnecessary coordination, which is the enemy of scalability. Right? This system can't run faster than this thread can run on the right side, so you don't want to make this a slow job if you can help it. All right. For our next lab, we're going to take the schemas that you created in the last lab and put some data in that matches. Put some example data in that matches your schema. The links on the, I am going to walk in front this time. The links on the right side of the page are examples of these things that you can use to cheat in a good way, right? And grab from those examples. So the CRUD example shows creating basic assertions and retractions. The component attributes section of the tutorial shows making entity maps instead of assertions and retractions. And after you do that for about 5 seconds, you'll never make raw assertions again because it's much easier to group things by entities. Then try modifying an existing entity. So this will get you in the business of how do I find the entity I just made? Right? And the obvious way to do it, by the way, is to look it up by having it have a unique ID. So put in a user who has a unique email or whatever, and then look them up by that unique email to do the modification. And then I doubt we're going to leave time for you to do this, but if anyone is super ambitious, you can create one of these transaction functions to act as, say, a constructor. So one of the things that relational databases do is you can say this table shape dictates what you can make. Datomic doesn't have a table shape. So if you want to dictate what somebody can make, one way to do it is by giving them functions. By giving them constructor functions that are installed in the database that say, I take these 6 arguments, I perform these validations, and I throw an exception if if I'm not happy with what I see in those validations. And so that example walks through doing that. All right. We will take a break for lab, and I will check the clock in a minute and let you know when we'll resume. Thanks.